right, so this is chapter 4, problem number 9. We're told that there's a 0.140, in other words, 140 gram baseball traveling at 35 meters per second when it strikes a catcher's mitt, which in bringing the ball to rest, the mitt recoils back 11 centimeters. We're supposed to figure out what is the average force applied by the ball onto the glove. As usual, let's start off with a picture. And this will be very good. So here's the baseball coming in. It's got an initial velocity of 35.0 meters per second. And we have our glove. And I don't know how many fingers are in the glove. Maybe there are 3. Need to go back to school for this. Okay, so that's the picture, right? That's before. Okay. Afterwards, the ball has made contact, the mitt has moved back a little bit, and so let's kind of draw that together. Ball and mitt together. Initially started at 0, but the mitt has moved back a certain distance from 0 to 11 centimeters. Okay, that is the displacement. And of course, at the end, the final velocity of the ball and mitt together are 0. Initially, looks like that. Okay, so we have the before and after picture. The good news is all this is happening in one dimension. So as far as concepts go, we can just use those one-dimensional kinematic equations that we've been using so far. Let's write down what it is again that we want. We want the average force, let me call that F average, force of ball onto the glove, or the mitt. They mean the same thing. Okay, so conceptually, what do we have? Concepts. We're talking about forces, so probably we're going to need Newton's second law, N2L. We're talking about forces of one object onto another, so we might want to keep in mind Newton's third law as well. Whether or not we'll need it, I'm not sure. And then lastly, because we have an object moving in one dimension, we're asked to get the average force. That probably means we need an average velocity for an object that's moving in one direction. So one-dimensional constant acceleration motion. Constant accel motion. That should be pretty good. Let's maybe make a little list of things that we know. We have the mass of the ball, 0.140 kilograms. We have the initial velocity of the ball. That's good. We have 35.0 meters per second. And we also have the displacement of the ball and the mitt together, 11 centimeters. Why don't we go ahead and write that as delta x as 0.11 meters, because we know we typically want things in kilograms, meters, and seconds, so that'll save us some trouble later on. The equations that we might need that correspond to these concepts, Newton's second law, remember F net is equal to ma. That's technically a vector equation, although we probably won't need to worry about that because we're just doing one-dimensional physics here. Newton's third law tells you that the force of object 1 onto object 2 is equal and opposite to the force of object 2 onto object 1. Lastly, constant acceleration motion. We're going to need those possibly 3 kinematic equations that we've been using for a long time. Let's write that as x is equal to x naught plus v naught t plus 1/2 a t squared. Again, I'm not putting any extra subscripts because we're only worrying about motion in one direction. V is equal to v naught plus at, and of course v squared is equal to v naught squared plus twice the acceleration times the displacement in the x direction. We're trying to get a force, and so let's think about what we need to do. The force, the net force acting on, at least on the ball, so on the ball, the net force is given by the mass of the ball. We'll write that like this for now, just using variables. Mass of the ball times the acceleration of the ball. We're given the mass, but we're not given the acceleration. That's something we're going to have to compute from one of these equations. Probably, given our set of choices here, we're not told what the time is, and we're not asked to figure out the time. And so we may find it to be easiest to use the third equation down here. So let's try that. To get the acceleration of the ball, the final velocity, That's known, that's going to be 0. The initial velocity was given, that's 35. The acceleration is what we want. The displacement is given to us as well, 0.16. So let's just go ahead and use this really quick. 0 is 35 meters per second squared plus 2a and the displacement of 0.11 meters. When you solve for the acceleration, it's a whopping 5,568 or so, give or take, with a minus sign. And if you think for a minute, you can convince yourself the minus sign is correct, because after all, the ball is starting off going in this direction. It's going to change its velocity. The change is in that direction. In other words, the acceleration should be in that direction, which we usually say is negative by convention. We have our acceleration. We have the mass of the ball. That means we can use this and figure out the net force on the ball is the mass of 0.14 times this big number here. And we figure this is approximately 780 newtons. We're almost there. We figured out the average force on the ball, but we're tasked with getting the average force of the ball onto the glove. That's where Newton's third law comes in. Remember, when you've got two objects touching each other, or even if they're not touching, they're just acting on each other, Newton's third law says that the magnitude of those two forces, 1 onto 2, 2 onto 1, they have the same magnitude, but they point in opposite directions. That tells you that you already know the force of the ball onto the glove. It has the magnitude of 780 newtons. It's just pointing in the opposite direction. Therefore, the answer is the net force acting on the glove, at least the magnitude of it, is approximately 780 newtons.